Okay, so it's a pleasure to have Mykhaylo Shkolnikov from Princeton University talk about the free boundary problem, probabilistic solutions and applications.
Thanks, Aviatar, for the invitation, and to Ron, who I think will come at some point. So I'll talk today about certain free boundary problems that have singularities, and more specifically about a new probabilistic way of solving these problems. And so I should say that this is based on joint work with a number of people, so mostly with Sergey Nadtochiy, but also with Francois Delarue, my PhD student Graeme Baker, and Sergey's postdoc Zhang. All right, so let's get started. So the outline will be roughly as follows. So I'll first focus on kind of the most prototypical free boundary problem that has singularities. It's the so-called supercooled Stefan problem. And so in the first part of the talk, I'll tell you a lot about this problem, so where it comes from. I'll explain how we can reformulate it as a question in probability, and explain exactly how we can solve it, so how we can show well-posedness of solutions and understand their structure. And then the second half of the talk, I'll try to argue that this probabilistic approach is actually much more general, and try to tell you the current scope of this approach. So I'll tell you about two more free boundary problems in one dimension. So one is the so-called Stefan problem with kinetic undercooling regularization and a certain two-phase version of that problem. And then I'll tell you about two problems in higher space dimensions, where again, probabilistic approach leads to new results. And finally, I'll tell you kind of what the future directions are, so where we're sort of headed with this agenda. All right, so let's get started. So I'll start with the supercooled Stefan problem in one dimension. But before I jump into the formulas, I'll want to show you a video of what this problem actually describes. So let me unshare the screen and share the QuickTime instead. One moment. Okay, and so what you will see in the video will be supercooled water. So that's water which is cooled below its equilibrium freezing temperature, so below 0 Celsius.
Black screen.
Yes, that's fine. The video will start in a moment. I just want to make a comment first, and then it will start. No worries. Yes, so supercooled water is water below 0 Celsius, which is still liquid. So you can easily create this kind of thing, for example, by putting a bottle of water in your freezer. And so what you will see in the video is what happens when you pour this kind of water into a glass, so when it touches some sort of surface. And so here we go. Right, so I guess, so the striking feature is that this video is in real time, right? And so whereas for usual water, you probably have never seen it freeze in real time like that. When you have supercooled water, you have typically this sort of instantaneous or very quick freezing. And this is kind of one reason why studying this problem mathematically or theoretically leads to interesting mathematics and interesting problems. All right, so I'll go back to my slides. So here we go. So the supercooled Stefan problem in one dimension goes as follows. So one dimension means that we think of the video you just saw, and we're just trying to understand how the frontier between ice and water was moving from left to right or right to left, depending on how you saw the video. So you just think of this frontier as a hyperplane that's advancing horizontally in one direction. And so in this problem, you have two unknowns. So one unknown is lambda. So that's a function of time, which describes the location of the frontier at any given time. And the second unknown is the function u, which describes the temperature in the supercooled water as this process evolves. Okay, and so the three lines of equations summarize the problem. So on the one hand, so the first equation is just the heat equation, which says that the temperature will evolve according to kind of the classical laws of heat propagation. And this heat equation is posed on a time-dependent domain. So it's posed on the domain, where you are to the right of the boundary lambda. So it's only posed in the water, which is usually referred to as a one-phase problem. So we're ignoring what is happening in the ice. In other words, we assume that the temperature in the ice is just exactly 0 Celsius, exactly the equilibrium freezing temperature, and we just model the temperature in the water. So that's the first equation. The second line has the boundary conditions for this partial differential equation. So on the one hand, you have an initial condition. So we start this experiment with some initial temperature distribution F. And we have a boundary condition, which is kind of the most classical one, which says that exactly at the boundary between water and ice, you are precisely at the equilibrium freezing temperature of 0. Okay, so that's not completely realistic, and I'll comment on that later, but most classically, you would make this assumption. And then the third equation is kind of the most intriguing one, so the third line of equations. So that's the one which connects how the domain changes to the temperature, and is known as the Stefan gross condition. And what it says is that the rate at which the ice will advance is proportional to the gradient of the temperature at the boundary. So depending on kind of how quickly the temperature decays as you look into the water, so the quicker it decays, the quicker the boundary will move. Okay, and I should also maybe emphasize that U here will always be the negative temperature, so the temperature below freezing. And so U will always be non-negative, and that will correspond precisely to the supercooled regime where the entire water is below 0 Celsius. Okay, so this will become important in a moment. Okay, so there is...
I missed something there, non-negative or non-positive. I mean, temperature.
Non-negative. So
you
yes,
measure the higher the function is, the colder you are. What's the...
Exactly.
Okay.
So U is the negative temperature. So U will be non-negative, but it will correspond to negative temperature.
Okay, that's why there's no minus on the heat equation.
Exactly. So okay. Otherwise, so of course one can flip signs and go from U to minus U everywhere. But
okay.
Then this will be more convenient. Yes.
Can I ask about the experiment itself? So what starts it seems like there is some initial condition, like some delta function somewhere that starts the spread. Is it something that is in the model, or is it understood?
So the initial condition is this function f that you see in the second equation. So basically, so in this equation, so everything would be at equilibrium if we had a constant 0 temperature at the water, in the water, right? Then you would get kind of the stationary solution where the frontier will not move. But because of the supercooling, so because this f will be some strictly positive function typically, so at least in some regions, this will trigger the solidification. Thanks. All right, so that's the problem, and it has a long history, and I'll be quick here, so I don't want to give you a long history lesson. So kind of Stefan problems in general go back as far as 1831. So originally they were about freezing of regular, not supercooled liquids. And so they were introduced by Lemma and Clapeyron, and then Stefan really started studying them systematically in 1889, and so that's why they're usually referred to as Stefan problems. And maybe let me skip the other historical references and just mention that, so for regular liquids, in some sense, the problem is completely understood. And so, one of the main papers there is a paper by Kamena-Moskaya from the 60s, which, gives sort of the correct notion of weak solution, proves that it is unique, and gives you also a numerical scheme to approximate it. So in some sense, sort of completely resolves the problem. Even though I want to mention that in terms of the fine structure of solutions, even in the regular Stefan problem, there's still new papers and new results coming out. So for example, there is a paper by Figali and Kosars as recently as last year. So there is still, something interesting to do even in that problem. Now for supercooled liquids, as far as I know, the first paper on those goes back to Sherman, so to 1970. And so what Sherman noticed and proved rigorously is that this problem has blowups, which makes it very interesting. And so what are blowups? So it has kind of for typical initial conditions, what will happen is that the rate at which the ice is advancing, so in other words, the speed of the frontier between ice and the water will go to infinity, so blow up at a finite time, right?
Sorry, what's the difference between regular problem and supercooled problem? What is the difference?
So the difference is just one sign. So in terms of the equation, so the difference is that in the last equation, so the equation for lambda prime, the sign, so in other words, the constant c that you see there would be negative in the regular problem, and for us, c will be positive. So mathematically, that's the only difference.
Thank you.
Yeah. Right, and so this kind of positive sign convention leads to these blobs, and that makes the problem interesting because, in particular, you cannot expect to have a classical solution to the PD even in one dimension. All right, so okay, so I'll go into the analysis of the problem in just a second. What I want to mention is that these kinds of free boundary problems and the irregular versions of those, so the supercooled versions of those, recently appeared in many different places, kind of independently of the experiment that I showed you. So one other place in physics is models of phase segregation. So in particular, the Jacomin-Leibowitz model, which is a model for how, for example, oil and water separate when you mix them together. And so the boundary between oil and the water will kind of, in a certain regime, will be described again by the supercooled Stefan problem. And then there are kind of all sorts of other places where this problem shows up. So one place is neuroscience. So I'll refer to papers by Francois Delarue and his co-authors, where this problem came up in the context of an integrate and fire model in neuroscience, and where these blowups again have a natural interpretation. So they would correspond to a certain synchronization phenomenon of neurons. So that's interesting kind of in its own right. This problem also shows up in hydrodynamic limits of certain random growth models, particularly the one by Dembo and Tsai. And it also came up in mathematical finance as a model of systemic risk. All right, so here, let me not dwell too much on the applications and go directly into the analysis. So the first observation I want to make about this problem is that you can rewrite it in terms of probabilistic objects. So instead of thinking about the PD, you can think about a problem in terms of Brownian motion. So here is how the problem works. So we encode the initial condition F, so the initial temperature distribution, as, so we think of it as the probability density of a random variable x0 minus. Okay, so implicitly I'm assuming here that F is not only non-negative, as I said before, but that it integrates to 1. And so for those initial conditions, the problem can be stated as follows. So we will still be looking for an unknown function lambda, which will describe the frontier between the ice and the water. And the problem will go as follows. So we'll try to find a non-decreasing function lambda with the property that if you start a Brownian motion according to x0 minus, you run a Brownian motion from this initial condition, and you keep subtracting lambda sub t, the resulting process x is supposed to have the following property. It's supposed to have the property that if I define its first heating time of 0, tau, the probability that my process hits 0 before time t should be given precisely by lambda up to a constant of proportionality, capital C. Okay, so in other words, you can think of it as a fixed point problem. So I'm starting with some candidate capital lambda. This gives me the process x and its first heating time tau. And then I'm checking if the CDF of this first heating time coincides with the lambda I started from. Okay, and so if I manage to kind of close this fixed point loop, so if indeed the CDF of the first heating time gives me exactly lambda up to this proportionality constant C, then I'm done and I have solved the problem. Okay, so let me explain why this is really equivalent to the problem I stated before. So, one way to argue this is as following. So let's forget about these blowups and assume that the frontier actually moves smoothly, and smoothly will mean C1 for me here. Okay, so then the process X is just a Brownian motion with drift lambda prime. And so if I think about the sub-probability densities, which give me the distribution of xt on the event that it has not been absorbed, then just kind of the standard forward Kolmogorov equation for x will tell me that these densities little p solve a certain PD. So that's the PD that you see towards the bottom of the slide, so the PD for p. And of course, the initial condition will be precisely f because I start my process according to f. And then, a slightly more complicated exercise. So, a two-line computation tells you that this fixed point condition, so the connection between lambda and the heating time, corresponds to saying that lambda prime is proportional to the derivative of p at 0.
So how does the probabilistic setup generalize this? Because you don't assume lambda to be differentiable anymore? That's essentially what's happening?
Yes,
Okay.
Yeah, that's exactly right.
Okay.
Yeah, thanks. I'll get to that in just a second. Right, so you end up with this PD problem at the bottom of the slide, and it already looks very much like the problem I had before. And so indeed, if you just make a change of variables and you basically shift the density little p by lambda, at any given time t, what you end up with is a function u, which will solve precisely the PD that we had on the previous slide. Okay, so in other words, solving the Brownian motion problem, which we refer to as probabilistic formulation, is the same as solving the original problem. As Sergey, yes.
Is uniqueness of the process trivial to see, or not?
Uniqueness of capital X?
Yes. Mm-hmm.
So, I mean, given lambda, of course, it's unique, right? So the big question is, right, is there a unique fixed point, so a unique lambda that satisfies this?
Exactly.
Right, and I'll get to that. I mean, this will be one of the main results for this problem. It's definitely not trivial. It's not trivial. No.
Okay, thanks.
Sure. Yeah. So, all right. So, as Sergey has already indicated, so the advantage of studying the probabilistic problem is that the derivative lambda prime does not make an appearance, and so you can now think about global solutions of this problem even in the presence of blobs. So even if lambda prime might be infinite, for certain points in time, this does not prevent you from trying to solve this problem for all time. Okay, so before I give you our main result about this problem, let me make some basic observations which should give you a little bit of intuition for how this problem behaves. So first of all, so the first bullet point is a stronger assertion that there are blobs. So what it says is that even if you have a very nice initial condition, so let's say CC infinity, so perfectly smooth, in typical cases, you will not find a continuous solution of the problem. So there is a very simple argument, a very short argument due to Hambly, Ledger, and Soymark that shows that, for example, if the expectation of the initial condition is too small, so below some threshold, like 1/2c, you cannot have a continuous solution lambda to the problem on the previous slide. And so what this tells you is that kind of the right space in which we should look for solutions is not the space of continuous functions, as you might have expected a priori, because Brownian motion is continuous, but rather it's a space that can accommodate discontinuities. And so for probabilists, sort of the natural space to look at is the Skorohod space, so the space of right continuous functions with left limits. Okay. Now, if you formulate the problem in the space D, you also fairly quickly realize that you cannot have a unique solution. And the reason for that is that the jumps of lambda are not uniquely determined by this problem, right? So you can see already at the initial time that if you are trying to match kind of lambda to the hitting probability, you might have kind of several initial jumps of lambda that will satisfy this fixed point equation. Okay, and so this leads to a concept of solution which we refer as physical. So that term goes back to the papers by Delarue. And what it says is that we will be looking for a solution in the Skorohod space D, which has the smallest possible discontinuities. Okay, so you have this lengthy formula at the bottom of the slide, but once you absorb it, what it tells you is that among all solutions that satisfy the fixed point condition, we choose, so whenever we jump, we choose the smallest possible jump, which is consistent with that condition. Okay, and sort of physically, it's indeed kind of the correct solution to look for, because having a bigger jump would mean that somehow the ice knows that there is cold water somewhere ahead, and would kind of move further, anticipating this cold water that is further away, which is not really what is happening. Okay, so the main result about this problem is now, I guess, 3 years old, and that started our research agenda here. So it's a joint result with Francois Delarue and Sergey Nadtochiy. And so what it says is the following. So it says that for certain initial conditions F, I'll come back to the exact condition in a moment, we indeed have a unique solution, so both existence and uniqueness for the probabilistic problem, and uniqueness is in the class of these physical solutions. So there is a unique solution which picks up the smallest possible jumps whenever lambda jumps. Okay, and the condition on the initial density F is that it's non-oscillatory. So one way to say it is that on every compact interval, it changes monotonicity only finitely often, right? So it can kind of oscillate at infinity, right? So you can have something like a sine type of function, plus a constant, which will make it positive. But you cannot have oscillations that approach zero. So you cannot have something like sine of 1 over x times x. So these types of things are excluded.
Sorry, cannot you show once more how the probabilistic problem is connected with the Stefan problem?
Sure. Yes. So that's kind of this slide here,
Oh.
right? So it's connected because right. So lambda is just the same lambda, and the connection to the temperature distribution u is that you go from the process x to its marginal distributions at different times t on the event that you are not absorbed, right? So in other words, you can think about the absorbed version of x, the process which is absorbed once you hit zero. And so the marginal distributions of that absorbed process have densities that describe the temperature distribution in the water. So P is basically the temperature distribution seen from the point of view of the boundary. So P will live on zero infinity, so it describes the temperature, x units away from the boundary. Thank you. Sure, you're welcome. All right, so going back to the main results, so both existence and uniqueness was new for this problem at the time. So uniqueness was completely new. Existence was new in this particular class of physical solutions. All right, so let me explain a little bit. So what is sitting under the rags? So explain, how we come up with this result, and so how roughly the proof goes. And this will also illustrate how actually the solution lambda behaves. So it turns out that so the key to proving uniqueness is to understand the regularity of lambda in detail. And it turns out there are 3 different regimes in terms of the regularity of lambda. So one extreme is the regular regime. So that happens. So if you add some time little t, you will see a regular behavior, so continuously differentiable lambda on some interval from t to t plus epsilon, if the water next to the ice is not too cold. Okay, and not too cold is quantified by the condition that you see in the middle of the slide. So Q is actually related to P. So it's basically the temperature distribution in the water, but at time t minus, so right before time t. And so if right before time t, so in the sense of the left limit, the temperature distribution goes to 0, so to the correct boundary condition at the boundary, and it goes to 0 fast enough, meaning that it goes to 0 at least linearly, and that's the condition in the middle of the slide, then we can show that you will see this regular behavior. So you will get a frontier lambda, which is continuously differentiable on a small interval past time t, so let's say from t to t plus epsilon. Okay, and so that's sort of the boring regime, because there you will solve the PD classically, and you will just observe a classical solution of the PD problem on the small time interval. Okay, so then there is the other extreme, which is the jump regime. So that's the situation where lambda will have a jump, so where your ice will advance discontinuously. And so that happens kind of in the opposite situation, so in the situation where the water is sufficiently cold next to the ice, which is quantified by the condition that you see in the first display. So, okay, so a slightly non-rigorous way of formulating this condition is to say that we look at the temperature right next to the ice, so exactly at the boundary, and there is a critical threshold, which is a certain number, 1 over c, so it relates to that constant we had in the problem. And so if the water is colder than -1/c degrees Celsius, then you will see an instantaneous jump. So this supercooled water will instantaneously freeze, and your ice will advance by a jump. Okay, so the rigorous version of this condition, so the sharp version of the condition is that you look at the CDF. So instead of looking at the temperature, you look at the integrated temperature. And so if the CDF has a slope which is bigger than 1/c, so if it goes above the line of slope 1/c next to the frontier, this is when you will see a jump. Okay, and the jump will be exactly to the point, to the first intersection point of the CDF and the line with slope 1/c. Okay, so that's kind of the other extreme. And it turns out that what makes this problem difficult is the regime which is in between. So these are not the only two possible options. So you have something between the regular behavior and the jumps, which one can call, let's say, a mildly singular regime. So that's the situation where, as you see in the first formula, the temperature at the frontier between the ice and the water is below this threshold of 1/c. So this function psi at 0 could be positive or could be 0. So you start either exactly at 1/c at the critical threshold, and then your water is just slightly warmer than that in the vicinity of the frontier, or you might be somewhere between 0 and 1/c. So both of these.
And then regular regime Qt is 0 in the point.
Exactly. So basically 0 is a regular regime, above 1/c is the jump regime, and here in this regime it's everything between 0 and 1/c.
Thank you.
Sure, you're welcome. And right, and so basically depending on where you are between 0 and 1/c, which is captured by this function psi, you will see a different degree of regularity of your frontier. So in a sense, the most typical case is that you're strictly between 0 and 1/c. So if that happens, your frontier will be continuous, but only Herder 1/2 regular. So it will have a square root type of behavior, which is natural in this problem due to Brownian scaling. But you can have all sorts of other Herder exponents if your temperature is exactly at 1/c. So if it's exactly at 1/c, this function psi that you see in the capital psi that you see in the second display is the integrated version of this little psi. And so really depending on how this function little psi behaves, you can get, all sorts of polynomial or even subpolynomial degree of Herder regularity. So it can be kind of arbitrarily bad. So the order, the Herder exponent can be arbitrarily bad, but you are still continuous. Okay, and I should also mention, so both in this regime and when you have a jump, once you go slightly beyond time t, so on the open interval from t to t plus epsilon, you're back to the classical regime. Okay, so this is sort of the key lemma that you need to prove.
That was true in the previous slide as well, right? In the second
exactly. That's exactly right. Yes, and so once you can establish that, you're essentially done. So it's not so difficult to get uniqueness of the solution, and to establish the existence. So to establish that only those three regimes are possible, the main lemma is what you see on this slide. So that's sort of the key to the whole paper and to the whole argument, right? So basically, sort of the situation which you need to rule out to convince yourself that there are only these three possibilities is a situation where you have oscillations. So where your temperature is exactly at 1/c and then starts oscillating. So you're not kind of going strictly below 1/c or strictly above 1/c, but you have sequences of points one which is above and one which is below. And so to rule that out, what we use is actually an argument from PDE, so analysis, so-called zero number argument, which allows you to argue that the number of monotonicity changes in the temperature distribution cannot increase over time. Okay, so if you run the full space, you would get kind of the most classical version of the zero number argument. So it would say that if you study the Cauchy problem for the heat equation, the number of monotonicity changes of the initial condition is an upper bound on the number of monotonicity changes at any positive time. And this is not so hard to see, say for classical solutions, because just by the maximum principle. And here it's a little bit more complicated because you have the free boundary, but the argument is roughly speaking the same. Okay, so let me maybe skip the applications to save some time. So just to summarize, so in this first problem, at the end of the day, the probabilistic formulation helps to, on the one hand, put the solutions in the right space. So to understand that you should study lambda in the Skorohod space. And secondly, basically tools from stochastic calculus and stochastic processes allow you to establish the exact regularity of lambda, and that's the key to uniqueness. Okay, so what I want to do in the remainder of the talk is to just give you a high-level overview of other free boundary problems where this sort of approach works and leads to interesting results. Okay, so yes.
Can I ask one more question about the modeling? So why is the heat equation only in one side of the frontier and not in both sides? So
yes, so we will get to that. So right, so it's only for mathematical simplicity, right? So these one-phase problems, they are just simpler to analyze because they give you a monotone frontier. But in a moment, I'll tell you a few things about two-phase problems as well. So in reality, you're absolutely right. So the temperature will change both in the ice and in the water. And of course, it has a non-trivial effect on how the solidification will happen.
I see. Thanks.
Right. So before getting into two-phase problems, one thing I want to mention is the so-called kinetic undercooling regularization. So in a sense, this problem on the current slide gives a more precise physical model, but it's more precise kind of in a different direction, not in terms of the two phases. So it looks exactly like the problem that I had before in terms of the first two lines, but it has a different condition for how lambda grows. And basically, so I will not go too much detail here, but basically what's this last equation, so somewhat long equation, is saying is that to trigger solidification, actually, it's not enough to be exactly at 0 Celsius, so exactly at the equilibrium freezing temperature. The water has to be slightly below that temperature to start freezing, right? Which, as far as I know, is the kind of more accurately corresponds to what is happening in nature. And so, you end up with a different boundary condition for the PD or a different condition for the growth of your ice. And what is interesting is that, so you have this epsilon sitting in the equation connecting lambda prime to u. So there is some epsilon here, which basically corresponds to this gap between 0, so the equilibrium freezing temperature, and the one at which solidification actually happens. And so if epsilon is small, this gap is small. So you can think of this problem as being, so this problem with small epsilon as being accurate for materials where the gap between the two temperatures is fairly small. And mathematically, what turns out is that when you send epsilon to 0, so when you close this gap, you, as you would expect kind of non-rigorously, you indeed arrive at the solution of the problem that I just described. right? So rigorously, we could only prove it now because to prove a limit result, you need uniqueness for the problem I was discussing before, the supercooled Stefan problem. And so only after proving uniqueness, we could give a rigorous argument that the problem with undercooling regularization really converges to the supercooled Stefan problem. And the interesting thing for probabilists, so probabilistically, is that the boundary condition here, again, corresponds to some natural probabilistic objects. So if you look at the second line from the bottom, so before we had this fixed point equation where lambda had to be equal to the cumulative distribution function of the heating probability of 0. So here, if you write the probabilistic formulation, it turns out that you end up with a different fixed point problem. And lambda here will have to be related to the local time that a process X, kind of like the one before, accumulates at the frontier. So this boundary condition here, instead of saying that we should absorb our Brownian motion when we hit, actually says that we should reflect on the frontier when we hit, and we should keep track of the local time that we accumulate there. And at the end of the day, so the PD problem above says that a certain functional of this local time has to be exactly equal to the lambda that you start from. And you know that this kind of naturally opens up a door to probabilistically show that the solutions here converge to the solution we had before, right? So it's at the end of the day, it's somehow a statement about convergence of this functional of local time to the cumulative distribution function of a heating time. So it's a purely probabilistic problem. Okay, so a few more things in this zoo of free boundary problems. So, you know, another.
Sorry, I want to ask.
Sure.
This new probabilistic representation, the particle will not be observed at all. Like, what happens if you send epsilon goes to 0 in your new model?
Right. So. Okay. Actually, yeah, what I said was not quite right. Yeah, thanks for bringing this up. So the exact process that you have goes as follows. So it will be reflecting on the boundary, as I was saying, but it will be actually absorbed when an exponential clock rings, and the parameter of that exponential clock is the local time you accumulate. Okay, so basically you can think of, you know, whenever you hit the boundary, you make it sort of more and more likely that you will be absorbed, and then eventually the particle will be absorbed. And the epsilon kind of tunes precisely this relationship, you know, how much time you need to spend on the boundary before you absorb.
The first time your local time exceeds an exponential time.
An exponential one random variable, exactly. And, you know, there is some multiplier of epsilon or 1 over epsilon, which tunes this relationship, exactly. Cool. So let me move on. So in terms of one dimension, there is one more thing you can do. Namely, you can study the two-phase problem. So that kind of goes back to one of Sergey's questions. So you can study the problem where indeed you model both what is happening in the ice and in the water in terms of the temperature. So the exact problem is here. So again, it looks kind of the same, just that the gross condition has now two terms. So one corresponds to the temperature gradient in the water and one to the temperature gradient in the ice. And there are kind of two regimes, was interesting. So one regime is where the two constants C1 and C2 have opposite signs. So that corresponds really to this phase transition setting. So that's a situation where basically both the ice and the water are colder than 0 Celsius. And the regime where C1 and C2 are both positive, so it doesn't make sense really in terms of phase transitions, because it would say that the ice is superheated, so above 0 Celsius, which does not really exist, and the water would be supercooled. But it's still relevant in this other setting that I had mentioned before, so in the setting of phase segregation, where you have a mixture of two non-mixing substances like oil and water, and those two, and you're trying to describe the separation of the two. So that would, at the end of the day, give you a free boundary problem with the opposite sign convention. And so, so here, currently, what we can do is show that you have existence of a physical solution, which we expect to be also unique. So the uniqueness is work in progress. The existence is already proved and published. And the difficulty with these two-phase problems, the additional difficulty is that in those problems, lambda is not monotone. So your frontier can go back and forth depending on how the temperature evolves. And this makes things more complicated. So, studying basically the fixed point problem I was talking about in the space of monotone boundaries is easier than looking at kind of generic CAD-like functions in the Skorohod space. So there are new technical challenges here as well. All right, so in the last 10 minutes or so, I want to say a little bit about higher dimensions also, because this probabilistic reformulation does work in higher dimensions as well. So I'll tell you about two problems in higher dimensions very briefly. So one is the exact analog of the one-dimensional supercooled Stefan problem that I started from, right? So here you're in some high dimensional space RD. So initially you have now a set which you assume to be closed, so some generic closed set, which describes the initial location of the ice. And your second component of the initial condition is a temperature distribution outside of that set. So that's the temperature distribution in the water, which we call F as before. And here the solution is now more complicated. So in high dimensions, we're looking for a process, so a set valued process gamma sub t, describing how the ice will grow over time, and a function of time and space u, which describes how the temperature will evolve. And so in terms of mathematical equations, so u most classically is assumed to satisfy the heat equation, so it's same as before, just in RD now. You have the same boundary conditions as in one dimension, and the gross condition is now just a high dimensional version of what we saw before. So at every point on the boundary of the ice, you will look in the normal direction. And so the gross velocity, capital V, in that normal direction will be given by a multiple of the directional derivative of the temperature in that same direction. Okay, so that's a natural high dimensional analog. And one thing that makes it immediately more complicated when you're in dimension 2 and higher is that we don't actually expect the boundary of gamma to be smooth, right? So already, this description of growth in terms of the normal direction to the boundary becomes, a bit dubious.
So is the normal at least well-defined most of the time, something like that? No?
Actually, we don't really know. So we don't really know that's the right answer, but I don't think we even expect it to be well-defined most of the time. So what you expect actually is, some sort of further continuous type of boundary. So in R2, think of the boundary as, roughly speaking, a Brownian motion type of curve. So it will not be smooth anywhere. So that's what we would expect. And so, right, so it's not clear at all what the normal would actually mean for that kind of boundary. Right, so what is written here would be the classical formulation, but of course, as already observed by PDE people before, this classical formulation will, you will not be able to solve this problem in the classical sense. So you need some sort of big formulation in any case. And so I guess the particular big formulation that we use in our work is, again, a probabilistic one. So again, in terms of a problem involving Brownian motion. And it goes as follows. So the key equation here is in the second line. And for simplicity, let's think of this function chi that you see on the left-hand side as just the indicator of the set gamma t, right? So it's just the indicator of the ice region at time t and evaluated at location x. Okay, and also, let's think of this function phi, the test function, for a moment as being identically equal to 1. Okay, just to get a sense for this equation, right? So in that case, if phi is equal to 1, we can drop it. And on the left-hand side, what you end up with is the volume of gamma t minus gamma 0 minus. So that's the volume growth of your aggregate, of your ice block. And the right-hand side, again, if I set phi equal to 1, would give me exactly as before a CDF, right? So it would tell me that the probability of hitting the ice block by Brownian motion has to be equal to the volume by which the ice block will have grown between time 0 and time t. Okay, so ignoring the phi for a second, your problem would go as follows. So the problem would be to find a set, so a process of growing sets, gamma t, such that the volume growth between time 0 and time t is equal to the probability that a Brownian motion started according to the initial condition f hits this growing set gamma by time t. Okay, and now what is the point of the test function? So the point of the test function is that, of course, in high dimensions, it's not enough to describe how the volume grows, right? That does not really tell you much about the geometry of the set. So the big equation in the second line is a local version of what I just said, right? So you should really think of phi. So for mathematical purposes, it's convenient to take smooth test functions, but think of phi as the indicator of some small ball, small radius. And then this equation would tell you that the rate at which the ice is filling the ball is equal to the probability that your Brownian motion will hit the ice block by time t, and that the point where it hits will be within the small ball that you're looking at. Okay, so it's kind of a local version of what I was saying before. Okay, and so, right, and so, okay, so the rigorous result we have about in this problem is in dimension d equal to 2. So in 2 dimensions, under fairly mild assumptions on the initial condition, what we can show is that there is a sub-solution, if you like, of the PDE problem. So there is a process.
Sorry, and what is delta gamma s on the previous slide? Delta gamma.
Okay. So so thanks for the question. So you remember already in 1 dimension we saw that there will be discontinuities, right? So points in time where the ice grows by a non-trivial amount, and so delta gamma s is the jump of the set gamma at time s, right? So you have this non-decreasing process of sets, and sometimes you will see an instantaneous jump, so your ice block will increase instantaneously by a non-zero volume. So this delta gamma s is that set, so that extra additional chunk that you add to your set at times. Okay.
Thank you.
Sure. Right, and so the result that we have is that you can prove that there exists a subsolution of this equation where the chi function on the previous slide is really the indicator of gamma t. So basically where you satisfy the local growth condition I had described, but only with an inequality, right? So this inequality is saying that the volume by which the ice will grow in every small ball will be at least that hitting probability that I described. So the hitting probability of Brownian motion, hitting the set within this particular small ball for all small balls. Okay, and so to explain why we only get the subsolution, let me just briefly say what we're doing. So we again, I didn't say it before, in fact, but so for the existence, what we do is we construct an approximating gross model. And so here, kind of the natural model to look at is a certain version of external diffusion limited aggregation. So that would look something like this. So here the initial condition is this ball in the middle. And so the black parts give you numerically the set so the aggregate after you run the discrete version of the gross process. And so, right, and so the reason why limit points of these gross processes only give you subsolutions in high dimensions is that in multiple dimensions, these processes create lots of microscopic holes, right? So your gross process is filling a square like the one that you see on the slide, not by kind of filling, let's say 99% of its area quickly, but rather it gets to the boundary of the square, and in terms of the distance to the black cluster, it will fill the square fairly quickly. But and so when you pass to the limit, because the holes in the black cluster will go to zero as you decrease the mesh of the lattice, in the limit you will fill the square completely, so you will grow by a fairly large area. But but in the pre-limit you haven't really filled out the square, and somehow so this discrepancy between filling a domain in terms of the distance to the cluster and filling the domain in terms of the area filled, this leads to this inequality and shows you that limit points of these gross processes in general can only give you sub-solutions. So we have in fact an argument saying that for certain initial conditions we can prove that the limit points do not satisfy the equation with an equality. So indeed, you don't really get the solution of your problem in general, but just a sub-solution. Okay, so I'm running out of time a little bit, so let me skip kind of the last problem I wanted to mention. So that last problem is kind of a version of what I was describing just now with surface tension. So where somehow the aggregate is more smooth because you have a curvature term entering the boundary condition. And so that problem, we think one can analyze more completely, even in higher dimensions.
Growth of drops, so to speak?
Say it again?
Growth of drops.
Yes.
Or,
well,
shrinking.
No, I mean, basically, I guess the one way to say it is that it's again kind of a more precise model of what is happening in nature. And what it says is that if you have an ice block and you try to understand how it will grow at a certain boundary point, if it is a point of high curvature, so if it is the tip let's say for long dendrite, then so to be in equilibrium with the water at that point, the temperature of the water has to be very negative. So it has to be very cold. So in other words, in reality, if the water is not that cold, you will have an accelerated growth. So you will grow more quickly at points where, sorry, I said it exactly the wrong way around. So when you create a long dendrite with a sharp tip, you will typically, start melting the tip. And when you have kind of a concave region, so let's say a fjord of water going into the ice, you will start filling this fjord. So that's what this curvature boundary condition is doing. And so in this problem, you expect a more smooth aggregate because these fjords and the tips, will be quickly eliminated whenever they appear. And so in that problem, we hope that you can get both existence and uniqueness biotechniques. And, as a test case, we did get existence and are currently completing uniqueness in the radially symmetric case. So it seems like we're making progress on that problem. All right, so I don't want to go too much over time. So I guess, let me just mention one future direction. So kind of the most interesting future direction, in my opinion, is to get well-posedness of high-dimensional free boundary problems where you have such singular growth. And we think that this problem with surface tension, so the one where the aggregate is more smooth, is kind of a good reachable goal for this agenda. And that, in that case, you can prove well-posedness on the one hand by using DLA type approximations to get existence, and on the other hand by studying the regularity of solutions of heat equations in time-dependent domains, like we did in one dimension, to get uniqueness. So that's kind of the big problem that we're working towards. And so all of these have also interesting applications, for example, in terms of modeling ice in the polar sea, which is part of climate change models. There are lots of interesting applications of all of this.
So the first point is, sorry for stopping you. The first point is since you had only an inequality and not equality, then you cannot go back from understanding the continuous solution and get some geometric understanding about this external DLA.
That's right. And I think, the conclusion here is really that these two are really different. So in fact, the typical limit points of DLA will be only sub-solutions. So understanding the continuous problem will actually, it will provide some insight about external DLA, but it will not really describe the scaling limit of external DLA. So these are kind of orthogonal, so complementary directions.
But does it give a bound on the growth of the discrete models?
Yes. So right. So I guess you can hope. Right. So it will give you a bound if you can understand the continuous solution well enough, and so it will give you. So for example, you can hope to get something like the Sidorovicius-Stauffer results on external DLA that, for high enough concentration of particles, you are growing, at a certain rate. So that the scaling, so you might be able to get kind of the scaling behavior of the diameter of your external DLA and things like that. But if you want to go kind of beyond that, so if you want really to understand the scaling limit of external DLA, then this approach basically is hopeless. I think so. That this will not give you the right answer. It can only give you bounds.
Okay. Thanks.
All right. So I wanted to stop here, and of course, I'm happy to take more questions.
So let's make a sticker over Zoom.
Thank you.
Any further questions? So I had a few more.
Sure.
So I mean, if given the continuous derivation of the problem, I would think that there should be some simpler discrete model that would approximate it, which is not something like as complicated this this MDLA, right? So something like having a random environment which would give you the fluctuations of the temperature, and then just you know, a simple some exclusion process or something like this in the, at least for the one phase solution. So
right, but I think in the end, so kind of the difficult thing, so in terms of these discrete processes, right? So think of some cluster, let's say in C2, and okay, you have some particles, maybe from an exclusion process, maybe a random walks. So the Stefan Gross condition is saying exactly that, you know, when a particle hits, you are supposed to grow, you know, by that side of that square, depending on how you define it. So in a sense, you know, you can try to find sort of the simplest possible driving process, but the way the aggregate grows is really according to this external DLA type of mechanism. So you're somehow so you're supposed to absorb mass, right? So absorb some process which is defined in terms of the temperature, and you're supposed to grow in terms of volume, let's say by exactly, you know, as many squares as the number of particles, or, you know, as the part of the environment that you absorb.
I see. So you cannot you cannot model it by like a random walk on a random conductance model, something like this, where the time of the right, the time of the moves is proportional to the conductances. It seems very similar to many things which are more classical than this.
Yeah, so I think, okay, I don't want to rule it out because, of course, I don't know all the possible models that are out there. But I think, you know, if you have some model based on, which is based on rates, right? So like what you're suggesting with random conductances, what I suspect is that you would end up probably with one of these regularized problems. So the one where, so that would correspond, yes. So maybe to a random walk, you know, running around in this random environment, and where, you know, you would not maybe immediately grow, but you would grow according to a rate, you know, described by the behavior of this walk. So,
I mean, if the conductances are not elliptic, you might get some blow-ups, which are similar, but these are harder to analyze. You can have like infinitesimal time that it will take you to diffuse in some direction.
Yeah, no, this is correct. Yeah, so I agree with that. So I think you can probably find some scaling of the conductances, which will give you this sort of singular.
It's not necessarily easier.
Right. No, but yeah.
Works of Deutschel,
that's a good point.
Yes.
No, that's a good point. So you might be able to do that. Yes.
Okay, interesting. Thanks. Are there any other questions? Okay, so let's thank our speaker again.
Thanks for having me.
Hope to host you in person soon.
Yeah, that would be great. Thanks a lot. And good seeing everyone.
Bye-bye. Great seeing you.
Bye.
Thanks for the talk.
Sure. You're welcome.
Bye.
Yeah, nice talk.
Bye. Thank you. Bye.
Bye.